Hello everyone, this is Rohan, and in this video I am going to show you how to find out the slopes and deflections in a cantilever beam using conjugate beam method. But before I start on with the numerical problem, I would recommend you to please first watch my introductory video to conjugate beam method. I have given the link for that video in the description below, as it will be useful for you to follow this problem. Alright, now let's start with the numerical problem. It says, find the slopes and deflections at points B and C for the cantilever beam as shown in the figure below. The value of E is given as 2 into 10 raised to the power 5 MPa, and the value of I is given as 5 into 10 raised to the power 8 mm raised to the power 4. So what we have here is a cantilever beam ABC with the fixed support at A and the free end at C. The portion AB is of length 3 meter, the portion BC is of length 2 meter. At B, there is a point load of 60 kilonewton, and in the portion BC, there is a UDL of 20 kilonewton per meter. Moreover, the moment of inertia of portion AB is 2I, and the moment of inertia of the portion BC of the beam is I. Okay, now what are we asked to find? We are asked to find the slope at B, the deflection at B, the slope at C, and the deflection at C. And we will have to use the conjugate beam method to find out these four unknowns. Now, the first step of conjugate beam method is to convert this real beam into a conjugate beam. Now, as we know, the conjugate beam is a fictitious beam of the same length as the real beam. So, as you can see, the length of the conjugate beam ABC is the same as the real beam, but the supports are not the same. If there is a fixed end, it becomes a free end, and if there is a free end, then it becomes a fixed end. So here in front of you is the conjugate beam for the real beam here. So the first step is done. We have converted the real beam into the conjugate beam. Now we will have to find out the M by EI diagrams for the real beam. In the next step, we will have to find the M by EI diagram. Now, for drawing the M by EI diagram, to simplify things, I am going to first find out the M by EI diagram for 60 kilonewton only. That means only for this point load, and I am not going to consider this 20 kilonewton per meter. Yes, of course, after this I am going to consider 20 kilonewton per meter, and then we will not consider this. So let's concentrate on 60 kilonewton first, and let's forget that there is any 20 kilonewton per meter here. So I am finding out the M by EI diagram starting from right to the left. So because of this 60 kilonewton, for the portion CB has no load. The portion CB has no load, so therefore the moment at C as well as the moment at B will be 0. But the moment at A will be 60 multiplied by 3, right? And please remember, this is not only M, this is M by EI diagram. So the M is 60 multiplied by 3, but it is divided by E multiplied by 2I. E multiplied by 2I. So this numerator is M and the denominator is EI, and if you solve that, it comes out to be 90 divided by EI. So I can simply join from B, it was 0, to 90 divided by EI, and I can finish this diagram like this. And just see, since it is right of section clockwise, so this will be taken as negative. So this is the M by EI diagram due to this 60 kilonewton only. Now, similarly, I am going to find out the M by EI diagram due to 20 kilonewton per meter. Now, please consider the 60 kilonewton is not here. Okay. Now, at the point C, the bending moment will be 0. At the point B, what will happen? It will be 20 multiplied by 2. That is giving the intensity. 20 multiplied by 2 multiplied by half of 2. Multiplied by half of 2, that is this distance from the CG of this load to B and divided by E multiplied by I. Okay, so that is 40 divided by EI, and this is going to be joined by a parabolic curve. This is joined by a parabolic curve. However, interestingly, if you see at B, the section is such that one part the value of I is 2i and on the other part it is I. So at B there will be two values of m by ei. One is what we have already found by dividing it by ei, and the other one will be the numerator remains the same, but the denominator will be e multiplied by 2i at the same point, and it will be like this. So this is 40 divided by ei, and at this point this is 20 divided by ei at the same point B. Now if I consider at A, what will it be? It will be 20 multiplied by 2 multiplied by half of 2 plus 3. That means the CG of this load from A. Okay, so that will be half of 2 plus 3 and divided by, obviously it is E multiplied by 2i, E multiplied by 2i, and if you do that it comes out to be 80 by divided by EI, and I can join this by a straight line and finish the diagram. And since all of these are right of section clockwise movements, so therefore again this diagram is negative, okay, because it's a hogging bending moment. This is negative. So here we have found out the m by ei diagrams due to both the loadings. If I would have found it together, it would have been a little complex, so it's better to take one load at a time and find out the m by ei diagram separately. Now the third step is that we will have to apply the m by ei diagram as a loading on the conjugate beam. All right, so here I have brought back the conjugate beam again. Just see that now the fixed support has shifted to C. Okay, so this is the conjugate beam, and here I will apply the loading. The first loading will be, yes, this 90 kilo divided by ei. Now please remember from my previous video that if the bending moment is negative, that means if the m by ei diagram is negative, then the loading will be in the downward direction. So therefore now this I am converting into a loading where the loading is in the downward direction. So what is this? This is a uniformly varying load, a UVL of 90 divided by EI for the span AB, right? Previously it was a M by EI diagram. Now I am applying the M by EI diagram as a loading. We will see it further in the next slide. So this was the M by EI diagram, right? This was the M by EI diagram for the second load, and of course that was also negative. So this m by ei diagram will also give rise to a downward load. Now this is a little complex kind of a loading, so I would like to simplify this. If you notice this portion starting from here, here and this, so this is a trapezoidal loading. It's a little difficult to compute, so what I'll do is that instead of dealing with the trapezoid, I am going to convert this into a rectangle and a triangle. So here this portion will become a rectangular load, which is nothing but a UDL, uniformly distributed load. And what will its be its intensity? It will be equal to this line. What is this? This is 20 divided by EI. So here also you will get 20 divided by EI. And now here the remaining one is a UVL, but its intensity will be what? 80 minus 20, that is 60 divided by EI. So what I did, I converted a trapezoidal load of 80 divided by EI into two loads, 20 divided by EI of UDL and 60 divided by EI of UVL. Now please concentrate on this part now in the portion BC. Here there is a parabolic loading. There is a parabolic loading of 40 divided by EI. Okay. Now we will see how to deal with that later. So now here in front of you, you have everything to find out the shear force and the bending moment at any part of the conjugate beam, so that you can find out the slope and deflection in the real beam. So having this diagram in front of you, we can start with the various computations here. But before that, let us find out the value of EI. E is given as 2 into 10 raised to the power 5 megapascal, which is Newton per mm square, and I is given as 5 into 10 raised to the power 8 mm raised to the power 4. So therefore it comes out to be 10 raised to the power 14 Newton mm square. But everything that we have in this diagram is in kilonewton and meter, right? So we have to convert Newton mm square to kilonewton meter square. So now to convert Newton to kilonewton, I am dividing it by 10 raised to the power 3, and to convert millimeter to meter, I'm dividing it again by 10 raised to the power 3, but since this is square, it will be 10 raised to the power 3 square. So what you have in front of you is EI is equals to 10 raised to the power 5 kilonewton meter square. Okay. Now with this, let's move on. We will have to find out first the slope at B in real beam is equal to what? As far we know as the properties of conjugate beam, it will be nothing but the shear force at B in the conjugate beam. That means if I am able to find out the shear force at this point, then automatically I'll get the slope of B in the real beam. Please see, this is the conjugate beam. So shear force at B in the conjugate beam will be slope at B in the real beam. Now please see, I'll take advantage of the cantilever situation here. So I will not find out the support reactions directly. If I come from the left to right, here automatically I can find out the shear forces without finding out the support reactions. But what is the sign convention of shear force? Left of section, I mean, if my section is here, if this is the left of section, downward forces are negative and upward forces are positive. Keeping that in mind, let's start finding out the shear force. The first shear force will be due to this loading. What will it be? It will be half into base into height. That is half into 3 into 90 divided by EI. Okay. Now second, this triangular load I am considering. Okay. What will it be? Again, minus half into base into height. Half into 3 into 60 divided by EI. And lastly, I am going to consider this rectangular loading, nothing but the UDL. So it will be only base into height. So minus 3 into 20 divided by EI. And of course, I do not have to consider this loading, as I am finding out at B and I'm coming from left to right. Okay, so if I calculate this, it comes out to be minus 285 by EI. Now putting the value of EI as 10 raised to the power 5 as we have found out here, the answer comes out to be minus 2.85 into 10 raised to the power minus 3 radian. Okay, why radian? Because it is a slope. We are ultimately finding out the slope. Yes, definitely it's a shear force at B in the conjugate beam, but ultimately we are finding out the slope at B in the real beam. Now please remember, in the sign convention it was told that if the slope is negative, right, then it indicates that the angle of rotation is clockwise. So therefore you should always write the answer like this: slope at B in real beam, theta B is equals to 2.85 into 10 raised to the power 3 radian clockwise. Okay, so we have found out the slope at B. Now let us find out the deflection at B in the real beam, that is YB. I'm going to find out the deflection at this point. It will be nothing but the bending moment at B in the conjugate beam. So we will have to find out the bending moment here. Again, I'm going to take advantage of the cantilever situation, and without finding out the support reaction, if I can come from right to left, I can easily find out the bending moment at B. Now, what is the sign convention for bending moment? Left of section clockwise is positive and left of section anti-clockwise is negative. Let's keep that in mind and let's take one load at a time. So first I am taking this load. The moment about B will be minus half into base into height, that is minus half into 3 into 90 by EI, multiplied by, suppose the CG is here, so this distance will be nothing but 2/3 of 3. So minus half into 3 into 90 divided by EI multiplied by 2/3 of 3. Secondly, I am taking this UVL into consideration. So it will be minus half into 3 into 60 divided by I. Again, the CG from this point is 2/3 of 3. All right. Again, now I am going to consider this rectangular load, the UDL. So it will be minus base into height, that is 3 multiplied by 20 divided by EI, and the CG from beam is B is nothing but half into 3. So that's it. Again, I do not need to consider this parabolic loading, right? So here if I calculate this, I get this as minus 540 divided by EI. Putting the value of EI, I get the answer as minus 5.4 into 10 raised to the power minus 3 meter. Okay, because we are finding out ultimately the deflection at B in the real beam. Definitely, this is the bending moment at conjugate beam, but ultimately we are finding out the deflection at B in the real beam. So this answer should come in meter. Again, if you remember the sign convention, it was said that if the deflection comes as negative, then that means the deflection is in the downward direction. So therefore, simplifying this, I write that the deflection at B in the real beam is 5.4 millimeter in the downward direction. This is how you should write the ultimate answer. Similarly, now we will have to find out the we have to find out the deflection at, we'll have to find out the slope at C. Now, slope at C in real beam, that is theta C, is nothing but what? It is the shear force at B in the conjugate beam. If you find out the shear force at C, we can get the slope at C in the real beam. So one at a time, if I take this loading is half into base into height, it is already there, minus this UVL minus half into base into height, this also you know. Then I am taking this 20 divided by EI multiplied by 3, right? This also was the same in the previous case. Now, something new. Because we are here at C, I'll have to consider this load also. Now, what is the intensity of this load? This is a parabolic load. This is nothing but minus 1/3 into base into height. 1/3 into base, that is 3. So, this is 2. Base is 2. Base is 2 and height is 40. Okay, so minus 1/3 into 2 into 40 divided by EI. If I calculate this, this is coming as minus 311.67 divided by EI. Putting the value of EI as 10 raised to the power 5, I get the answer minus 3.1167 into 10 raised to the power minus 3 radians. Again, as per the sign convention, if the slope is coming as negative, that means the rotation is in the clockwise direction. So slope at C in the real beam is nothing but 3.11 into 3.1167 into 10 raised to the power minus 3 radian in the clockwise direction. The only difference between the slope at B and slope at C was this term, right? Rest of the terms were the same. This term minus 1/3 into base into height. This is all that got added. Okay, so that's why I was a little fast here. So now and the last thing that we want to find out is the deflection at C in the real beam, that is YC. We can find that by finding out the bending moment at C in the conjugate beam. So we are going to find out the bending moment at this position here. Again, one by one, if I take this loading, it is half into base into height, but now the CG has to be calculated from here. So 2/3 of 3 plus 2, as you can see here, 2 plus 2/3 of C is the distance from the CG to this point, isn't it? Similarly, for this triangular load also, half into base into height, that remains the same, multiplied by 2 plus 2/3 of 3. 2 plus 2/3 of 3. Okay, for this rectangular load, the UDL, it is minus base into height, that is 3 into 20 divided by EI, and multiplied by 2 plus half of 3. Okay, so 2 plus half of 3, and ultimately for this is something new. Okay, minus 1/3 into base into height, that you already know from the previous slide, but the CG is at a distance 3 by 4 from this end. So here the CG is 3 by 4 into 2. For a triangle it is 2/3, and for a parabolic load it is 3 by 4 into 2. Okay, so this is something for you to remember. If I solve this, I get the answer as minus 1150 into minus 1150 divided by EI. Putting the value of EI as 10 raised to the power 5, I get my final answer as minus 11.5 into 10 raised to the power 3 meter. Now, as per the sign convention, if the deflection is coming as negative, that means the deflection is in the downward direction. So you have to write your answer like this: 11.5 mm in the downward direction. All right, so this was the problem in front of us, right? This was the real beam, and with the help of conjugate beam method, we have found out the slope at B, the deflection at B, the slope at C, and the deflection at C. Now quickly I would like to show you how to actually show this in a diagram. So I will draw the deflected shape of this beam. Okay, so that's why now I am drawing ABC as a dotted line. That means this was the original position, but after the loading the deflected shape would look something like this. Okay, and here I am renaming the points. Just see that C has become C dash, B has become B dash, but A remains as A. Why? Because A is a fixed support. Here no slope is there, no deflection is there, so therefore no change in A, but B becomes B dash and C becomes C dash. Now to show theta B and YB at the point B, I will draw one horizontal line which shows its initial position. So therefore the theta B will be nothing but this angle. Can you see it? I'll do it again. Theta B is nothing but this angle. The original position was straight, but after deflection it became like this. So this is theta B. And as you can see, this is, compared to the original position, it is in the clockwise direction. Now this distance B dash is nothing but YB, and as you can see from your original position, this is downwards. Okay, this is clockwise, this is downwards. Again at C dash, I would like to draw a horizontal line as well as extend this curve further so that I can show you what is theta C. So theta C is this angle, right? As you can see from the original position, again this is in the clockwise direction, and this C dash is nothing but YC. So as you can see here, this is the deflected shape of the beam, and all the four unknowns theta B, YB, theta C, YC is shown in the figure, and it is easily cross verifiable based on the signs of the rotation as well as the direction of the deflections that we have got. Alright, so I hope you have understood how to find out the slopes and deflections of a cantilever beam using conjugate beam method. So if you have any questions, you can write in the comments below. Thank you for your attention.